In the first 6 lectures of differential equations and linear algebra, we've done a lot of applications to both difference equations and differential equations. Starting here in lecture 7 and going for a few lectures, we're going to get kind of theoretical, but the theory is still pretty important, so make sure you pay attention to a lot of subtle details again. Lecture 7a is about something called implicit solutions of ordinary differential equations. That's something new. Slope fields made from contour maps. We've talked about slope fields before, but I'm going to talk about a more systematic way to think about them here. And then we're going to start talking about some theorems, some existence theorems in this case. Starting in lecture 8, we'll also look at uniqueness theorems. Then in lecture 7b, it's the linear algebra. We're going to look at matrices and linear transformations, especially visualizing them in low dimensions. All right, so let's start with a problem where we have to use what's called an implicit solution. What if you do separation of variables and you can't solve for y? Here's a fairly simple example where that happens. dy dt equals 1 over 3y squared minus 1, and we'll also solve the initial value problem that goes to the point 0, 1. Use separation of variables to solve this. You should take the time to try it. Go ahead and pause the video and see if you can do it. This is an autonomous equation. The right-hand side only depends on y. There's no t's. All autonomous equations are separable. We can, in this case, multiply both sides by 3y squared minus 1 to cancel it from the right side and get it on the left. And we can pretend that we're multiplying both sides by dt to get the t on the right instead of and cancel it on the left. Here are the details. I hope that you did something to this effect. So first, again, separate variables like I just mentioned. So you get 3y squared minus 1 all times dy equals dt. This is something that when you look at it, you should feel like, oh, I need to integrate this. And yes, you should go ahead and integrate that. Integrate both sides. Certainly when you integrate the right side, that's easy. You get t plus some arbitrary constant. And the left side in this case is pretty easy to integrate as well. You get y cubed minus y plus some constant, but that can be absorbed into the constant on the right. But wait a minute. Maybe you scratched your head when you came to this point. What do I do? How do I solve for y? I was never taught how to solve general cubics for y. Well, yes, it is a difficult thing. I will show you the answer. I will show you that you actually can solve for y, but it's not a very pretty function. It's kind of ugly looking. So let's just leave it like this. And let's go ahead and call it a general solution, even though I put question marks there. This is an example of an implicitly defined function. This equation defines y as a function of t, not explicitly, not with some simple formula, some simple function of t, but implicitly with a formula you can't seemingly solve for y. Let's keep going. Let's look at the initial condition. Y of 0 equals 1. What do we do with the initial condition? We usually solve for c. What would happen in this case? Well, you'd want to take this equation and you'd want to replace the y's with 1 and replace the t with 0. What would you get when you do so? I'll put the work over here. You get 1 cubed minus 1, which is of course 0, on the left side, equals t, which is 0, plus c. But yeah, this is 0, so evidently c is 0. And so I guess we should write the unique solution of the IVP in this way. But again, I'm putting question marks because it's a bit confusing. We haven't explicitly solved for y as a function of t. Another weird thing about this is that this equation would actually solve another initial value problem, actually a couple other initial value problems when t equals 0. Can you think of what they would be? The graph of this equation would go through the origin. When t is 0, y is 0 also satisfies that equation. And moreover, when t is 0, y can be negative 1 as well. Negative 1 cubed is negative 1, minus negative 1 is really plus 1, negative 1 plus 1 is 0. This implicit equation evidently solves 3 different initial value problems when t is 0. That's kind of weird. So what do we do with this? What have we done? And can we do any better? Can we explicitly solve for y as a function of t? And I am going to focus on this particular initial value problem. It turns out you can, but again, it's a very nasty looking formula. You have to solve a general cubic. And if you've ever studied that, it's nasty. We'll get to that in a second here. It does depend on what you mean by better. This is a fairly simple equation. And again, when we solve for y as a function of t, it's going to be kind of complicated. So it does depend on what you mean by better. Technically, yes, it is possible to solve for y as a function of t. You want to see the answer? Are you sure? Here it is. Yikes, who would ever expect that? I didn't expect it to look exactly like this by any means. I knew it might involve some square roots and some cube roots evidently, because I've had a little bit of experience with this. I used Mathematica to help me solve that. You could try using Wolfram Alpha if you like. Yikes. Trivial, right? That's a joke. Actually, I want to tell you a little story here. My hardest class ever in grad school in math was a class called Algebraic Topology, and we were studying something called spectral sequences. Now, if you want to look that up, spectral sequences, it sounds like it should be a physics topic, but if you look it up like on Wikipedia or something, you'll see that it's actually a math topic, and as you scroll down, you'll see it looks like maybe the hardest topic you've ever seen. Anyway, my professor in that class would draw these huge diagrams all over the board. He'd be lecturing to the board, not really to us, but every once in a while he'd turn around and he'd look at us and he'd go, trivial, right? And we were like, uh-huh, not really. And I feel the same way here, and maybe you do too. It's not really trivial. Anyway, somewhat surprisingly, through the use of imaginary and complex numbers, it turns out that the domain of this function can be found to be something kind of actually unexpected to get real outputs. It's the set of all numbers t such that t is greater than or equal to -2 over 3 root 3. Now, I'm not going to show you the details, but if you try to think about it simplistically and think about, okay, I want the thing under the square root to be greater than or equal to 0, you actually will not get this answer, though it's related to this answer. So I'm not going to show you the details of that, okay? You're just trying to accept it here, and that would be the domain that you could verify is true for this case, okay? So again, don't try to do it on your own. We're going to get Mathematica to help us graph this, but at the moment we're just appreciating, if you can appreciate such a thing, how beautiful that function is. Isn't it beautiful? And again, that's going to be the domain. Remember this number. -0.3849 here, by the way, because a couple slides from now, we're going to try to mark off that number on an actual graph. I'm going to go ahead and write it down over here so we remember it. -0.3849. All right. So let's continue. More simply, we could just use the original implicit equation. It's certainly a simpler looking equation. And say the initial answers are implicitly defined functions where we don't explicitly solve for y as a function of t. In other words, my implicit general solution is this equation, y cubed minus y equals t plus c. For all t in some appropriate interval depending on c. And my implicit unique solution of the IVP is y cubed minus y equals t. C ended up being 0. Where I'm thinking about this particular initial value problem, y is 1 when t is 0. Again, you could also do y is 0 when t is 0, or y is -1 when t is 0. And again, t is in some appropriate interval. We're not specifying what it is. We're going to see graphically that you can estimate what the interval is from a graph. All right. We're about to get more theoretical here. Hang with me. Pay attention to details. If we let capital F be a function of two variables, f of t comma y equals y cubed minus y minus t. What in the world am I doing there? I'm essentially just taking this equation and subtracting t from both sides and thinking of the expression on the left-hand side as being a function of y and t. This equation right here is equivalent to y cubed minus y minus t equals 0. I'm going to think of that as a function of two variables, a multivariable calculus function. The variables being t and y. Not thinking about differential equations, actually, when I think about this. But now I'm about to think about differential equations, and I think about the initial condition. Y of t0 equals y0. It's an arbitrary initial condition that I'm thinking about here. For our example, t0 will be 0 and y0 will be 1. Then something called the implicit function theorem, which I'm not going to state, because it's kind of complicated. I want to try to get across the main point of the theorem symbolically here and then graphically soon. Guarantees that this implicit general solution and also the implicit unique solution defines an explicit solution. Explicit solution, y equals phi of t, call it, for the initial value problem for all t in some open interval containing t0. If two conditions are met, if when you plug the initial values of t and y into capital F, you get whatever c is. I guess I am talking about the general solution here. And if you take, what's this thing? That's a partial derivative. If you take the derivative of capital F with respect to y, treating the t as if it's a constant. Funny looking d there, kind of a pretty d, but funny looking. That's just a notation for partial derivative. You just pretend the t is a constant. It's not a big deal. And if you plug in the particular point that you're talking about, you get something non-zero. Then this implicit equation defines an explicit solution. Kind of abstract. In the context of this initial value problem, these conditions are equivalent to these. The c is 0, there's the c. There's t0, that's 0. There's y0, that's 1. That equals, well, when you plug it into the function capital F, replace t with 0 and y with 1, you'll get 1 cubed minus 1 minus 0, which is 0, which is c. And yes, the partial derivative of capital F with respect to y, treat the t like a constant. If you differentiate with respect to y, it differentiates to 0. This part differentiates to 3y squared minus 1, which is what you see there. Plug in the initial point, 0, 1, into that. There's no t's there, so you just plug in y equals 1. You get 3 times 1 squared minus 1 is 3 times minus 1 is 2, which is non-zero. Okay, so we verified this abstract, confusing statement in this context, but what does it really mean? What's really going on here? That's where visual, intuitive, graphical understanding can come into play. Qualitative understanding, which is a big point of emphasis for this course. I mentioned this near the first few lectures. We want to emphasize thinking about things graphically. We have done that to some extent so far with slope fields, but we've done symbolic things like separation of variables too. The right-hand side function for the first order autonomous ODE, the example we've been thinking about here, remember, is this function right here. Remember that was the right-hand side? The equation was dy dt equals 1 over 3y squared minus 1, and we separated variables. We have talked about how the graph of this function can help you draw the slope field. If you've been watching these lectures, we have talked about that. This graph can help us draw the slope field. What does the graph of this look like? Well, it's a rational function. Oh boy, we're going to have some vertical asymptotes. This is not a very typical kind of example graphically, but hang with me, we can still do it here. There's the graph of it. Ignore the y prime for the moment. This is a graph of this rational function of y. It's got no horizontal intercepts. Notice the horizontal axis is labeled with y. That's not a mistake. That's done on purpose here. The function is a function of y. This function is never equal to 0. It does have vertical asymptotes where the bottom equals 0, here and here, which if you think about it, 3y squared minus 1 equaling 0, that would be when y squared is 1/3, or y is plus or minus 1 over root 3. That's what where these vertical asymptotes are going to be. Think about this. This is y prime, yes, if you want to relate it to a differential equation, dy dt. The values of this function determine the slopes, dy dt, of solutions for the differential equation. Where this function is positive, slopes of solutions are positives, and where this function is negative, slopes of solutions are negative. But remember, when you draw solutions, y becomes a vertical axis. Here, y is horizontal. This is pretty confusing, but it is key if you want to understand things. And evidently, in this case, because of these vertical asymptotes, the slopes of the line segments, I guess, must approach plus or minus infinity as y approaches where the bottom is 0 here. Plus or minus 1 over root 3, which is about plus or minus 0.57735. Here's negative 1, negative 0.6 is about here, negative 0.57735 is right, a little bit to the right of where I drew it there. Positive 0.57355 is a little bit to the right of where I drew that there. This is the right-hand side function is getting high in value either positively or low in value negatively. Slopes are getting very steep positively or negatively, or approaching plus or minus infinity, I guess. What in the world is going on with that slope field? Moreover, the slopes are positive when you're to the when the absolute value of y is bigger than square root of 3 over 3. In other words, when you're over here or over there. And negative when the absolute value of y is less than square root of 3 over 3, when you're between these two vertical asymptotes. That's where this function is negative. Here's the slope field. We're about to look at it. We're going to see the solution that we found. And remember this number? That was going to be, it's going to come up here. For the IVP where y of 0 equals 1. And we're also going to see the full implicit solution, which fails the vertical line test. It's the brown graph is the full implicit solution. It fails the vertical line test. There are vertical lines like right there that go through it more than once. It's not the graph of a function. It's the graph of a relation. Graphs of functions of t have to pass the vertical line test. No vertical line goes through them more than once. And that does happen with the red graph, which is our phi function. It is our solution that the implicit function theorem was guaranteed to exist. And notice that evidently the left endpoint of this point right there, negative 0.3849, right about there. Right, there's negative 1 right there, negative 0.2, negative 0.4, we're pretty close to negative 0.4 there. And the second coordinate, that's the t coordinate of that, the second coordinate of this is positive 0.57735 approximately. And yeah, look at those slopes in the slope field. They're getting close to vertical near this line. No vertical lines are drawn, but they're getting close. And this solution, evidently, has a slope that approaches infinity as t approaches this number from the right. I guess you would say actually this solution fails to be differentiable at this number. But that's only one point. Maybe we shouldn't worry about it. And that is the perspective that people take. Lots of subtle details here. You may want to rewatch it, rethink about it, but these are important. Okay? If you really want to understand things both symbolically and graphically. And again, the graphical perspective is easier, right? It's less abstract, it's more concrete. You can see it. This is an autonomous equation. The slope field does depend only on y, not t. Along any horizontal line, the slopes have the same slope. And yes, they are approaching infinity along this horizontal line and along a horizontal line right about here at negative 0.57735. And yes, technically when a graph hits that horizontal line either here or here, technically it's not differentiable there, so you might say technically it doesn't solve the differential equation there, but close enough. It's just one point to sort of add to the domain of the function. And yeah, the whole graph, the whole brown graph, not the graph function, it's the graph of relation. It is the graph of y cubed minus y equals t. Equivalently, it's the graph in brown here. I don't have a brown option here. Brown graph is the graph of y cubed minus y equals t. Equivalently, it's the graph of capital F of t comma y equals 0. Because remember, we defined capital F by subtracting t from both sides and saying it's the expression on the left side after I do that. And that would be equal to 0 would give you that graph. This is called a level curve of this multivariable calculus function. That's going to come back in our next example here. So you want to pay attention to that kind of thing too. And it does go through 3 points when t is 0. So there's really 3 initial value problems when t is 0 that this solves. That's not usually the case in what we've seen so far. Okay? And we can draw other solutions. The slope field shows you other solutions. And if we're after functions of t that pass the vertical line test, then we're only looking at pieces of these graphs. Something like this would be a solution. Something down here would be a solution. Up until we reach those points where the slope field is vertical. But again, we could also look at more level curves of capital F, like where does it equal 1, to get more implicit solutions that are relations that fail the vertical line test. All right, so now we're going to look at our second example, and this is going to reinforce these contour maps and slope fields. Now we're actually going to look at a non-autonomous equation. It's also going to be not separable. Contour maps, which are graphs of a bunch of level curves for multivariable calculus functions, can help us draw slope fields and see the qualitative behavior of the solutions. So this is where we're moving on to thinking more about slope fields and being a bit more systematic in how we think about them than what we've done so far. So we're going to consider this ODE. It's a first order equation, ordinary differential equation. First order because it only involves the first derivative, not a second or higher derivative. It is nonlinear. The important thing that makes this nonlinear is the nonlinearity in y, the y squared. If this were a t squared plus y, we'd actually still call it a linear equation, even though t squared is nonlinear. That's an important point that we're going to emphasize in some future lectures. It's the y squared that makes this nonlinear. And in those future lectures, you will see why. That's the important thing to focus on. It's not separable. If you try separating variables to solve this, good luck. You won't have success. You could say, hey, well, couldn't I multiply both sides by dt and subtract y squared from both sides? Well, the problem is things get mixed together. You can try. You won't be successful. So the solution to this is difficult to find. In fact, there are solution formulas, but they involve functions you've never heard of before, Bessel functions and something called the gamma function. I'll show you in Mathematica, and this will be a chance to review Mathematica from lecture 6a, which was all about Mathematica. Let's see here. So I'm not going to take the time to type the code here. I pre-typed it. The main thing we're going to focus on is the use of DSolveValue in this case. That was an example command that I showed you last time, though I will highlight a few other things. Remember, as I mentioned in lecture 6a, to define a function, you use square brackets instead of parentheses for the input. When you first define the function, you need an underscore. That's essential. Colon equals is optional. You could just use an equal sign. Here I've defined the function. The semicolon just separates lines of code. All of this code is going to make a plot of this function. This is the plot command, and this is all the stuff inside here is the input for the plot command. I don't need all of that. I could make a simpler. Let me just go ahead and enter this to see the graph that was on the PowerPoint. I could make a simpler plot that is easier to type by doing just this much. There we make a plot, but you know, it's not as nice looking. It's not as thick for the graph. I like it making it nice dark red there. I like labeling the axes. I like making the axes thicker, bolder, okay, that kind of thing. So all the other stuff is just to make it look nice and to label the axes and label the graph instead. Actually, the vertical axis I'm labeling with y prime equals f of y equals 1 over 3y squared minus 1, like you saw in the PowerPoint. Anyway, that's a plot command. Let's focus on the DSolveValue. I have defined the function f already. So once I've defined it, again, like I do in the plot here, I don't need the underscore anymore. I can use it. I can solve the differential equation. This is the previous example, by the way, not the example we're about to do. This is the previous example. It's giving me a little warning. You don't need to worry about the warning here too much. This is a form of the general solution. I can also add an initial condition, y of 0 equals 1. Notice the double equal signs. That's something I mentioned in lecture 6a. To solve for my solution, and I don't know why it's giving me such problems here. This didn't happen ahead of time. Okay, let me clear the kernel. Whenever weird things happen, it's good to quit the kernel. Probably there's something that's in memory that's messing things up. Let's just see. This worked for me nicely ahead of time. Okay, I don't know why it's giving me such issues here. I wasn't getting this before. Anyway, this is kind of a crazy function. That is our solution. And here I'm defining it as a function of t. And here's my capital F function. So I can do all this and I can make the plot that you saw. There it is. Now let's look at the new example. Now I've got a function of t and y. That's the right-hand side function. Right? Remember, right-hand side functions are not solutions. They are right-hand side functions. They help you figure out what the solutions are, symbolically or graphically, but they're not the solutions themselves. Here's what DSolveValue produces. Here we're finally to the Bessel function and the gamma function. Bessel J, Bessel J, Bessel J. What in the world? And if you solve the initial value problem, it does it in terms of gamma functions as well. Bessel J and gamma. What in the world's going on there? That's just functions you've never heard of before. There are plenty of functions you've never heard of before that you don't learn about in pre-calc and calc. Bessel functions and gamma functions are some of them. And this code makes the graph that we're about to show you in the PowerPoint here, okay? So that's a little bit of Mathematica here. We can draw the slope field reasonably quickly by thinking about this contour map of this right-hand side function, which is a graph of many of its level curves. Now realize something, we're doing something different here than the previous example, besides the fact that this is non-autonomous. In the previous example, we graphed a level curve of a capital F function, which was different than little f. The little f was the right-hand side of the differential equation. The capital F was a function related to the implicit solution. Here I am talking literally about the little f, the right-hand side function right there, t plus y squared. I can still make its contour map. I can still draw its level curves. It's still a multivariable calculus function. Here's what its full graph looks like. In three-dimensional space, you need to think about this. So you want to, based on the labeling here, the t-axis is actually pointing in this direction. It's this black line right there, positive to the right. The y-axis, this is a function of t and y, is this one right there. Going into the screen is the positive direction. And the vertical axis is just the outputs. Well, you could call them y prime, I guess. I didn't do that here. Those are the outputs of this function. As t and y vary over the plane of my hand here, the outputs vary in value, sometimes positive, sometimes negative. And if you plot a bunch of points and try to connect them with a smooth surface, you'll get this kind of picture. Now that's kind of pretty, but it's kind of hard to understand real well in terms of these things called level curves, at least. We do see that as t increases, the outputs increase. We see as y increases or decreases, the outputs also increase. But what are the level curves that I'm talking about? I'm going to show you in the next slide a nice picture of this, but let me try to draw them a little bit by hand. What we want to do is we want to make a ty plane and draw some curves in this plane. Sorry, it's not showing up very well. Let's try it over here more. Draw some curves in this plane that are curves along which this little f function is constant. Takes on different constant values like 0 or 1 or 2 or -1 or -2. Let's think about where it's 0. Where does little f of ty equals 0? That's equivalent to saying t plus y squared equals 0, because that's the formula for little f. And that's equivalent to, if you solve for t, to saying t is -y squared. How do I graph that? T is a function of y here. T is horizontal, y is vertical. That's the opposite of what we're used to. But we can still think about it that way. We can think of the y-axis as being the independent variable, what we plug in, and the t-axis as being the dependent variable. Again, the opposite of what we usually do. And I guess if you think about it that way, and if you plot some points, you'll see that the graph is a sideways parabola. And the t-values have to be negative, because it's a -y squared. It's got to be about like this. That's where little f, its output equals 0. Now this is kind of abusing notation here, but it's simpler. This is the set of t's and y's where the output of this function, little f, equals 0, because it's equivalent to these equations. We can also think about where it equals 1. Where does this equal 1? That's equivalent to t plus y squared equaling 1, which would be equivalent to t equaling, sorry about that board here, t equaling negative y squared plus 1. T could be positive. It could be up to 1 when y is 0. It's a sideways parabola that looks about like this. That's where f equals 1 value. And I could do it for 2 and 3 and 4 and negative 1. If you think about it, t equals negative y squared minus 1 would be where f equals negative 1. A sideways parabola about like this. These are the level curves of f. Now, how does this help us with the differential equation? With the slope field. It tells us the values of the right-hand side function, which are going to be the slopes of solutions. In particular, the slope of solutions, if I think of this as a slope field, now I haven't drawn the slope field, but if I imagine trying to draw a slope field here, the slopes of solutions are going to be 0, for example, along this parabola, this sideways parabola. They're going to be negative over here, for example, like this, negative 1, in fact, and positive over here, positive 1, in fact, all along these curves. You're going to have constant slopes. Instead of, as with the autonomous equation, we had constant slopes along horizontal lines, here, for this example, we have constant slopes along sideways parabolas. And that could help you draw the slope field, and could help you draw solutions. For example, one solution might look about like, you might guess would look about like this or something like that, following the slope field. As a rough guess. Now let's look at a more precise picture that I made with Mathematica. Better pictures here. The values of little f determine the slopes of the slope field of the differential equation. The solution with the IVP is going to be shown in the picture I'm about to show you. Here it is. So this picture on the left is the pure contour map, graph of a bunch of level curves of the function little f. I can think about such a diagram without thinking about differential equations at all. It's just multivariable calculus, like I just did. And I've got the different level curves for the different values, the different output values of f labeled. This is f equals negative 4 here, negative 2 there, 0, 2, 4, 6, 8, 10, etc. Because the differential equation says those right-hand side values give you the slopes of solutions, we draw our slope field. Along any one of these level curves of little f, you draw a bunch of slope marks with the appropriate slopes. So, for example, along this particular one, you see slopes there, and approximately there, and here. They're going to have slope equal to 2. Those slopes should look like they're about 2. And you have 0 along here, like you see pretty close, well, in here, you don't see anything exactly 0, but in between, along this one, you'd have slope marks with slope equal to 0. Over here, like, for example, right here, the slope is approximately 10. And yes, I had Mathematica also draw in a solution, the solution of the IVP with y of 0 equals 1, goes through that point right there, is what you see. Okay, so this is a systematic way of making slope fields, though to make them nicely you still need technology. Why am I talking about this when I also talked about implicit solutions? Well, it's still related to implicit equations, contour maps, graphs that are not graphs of functions. That's one reason. Another reason it's an important thing. A third reason is that it helps you believe solutions exist. You just have to follow the slope field, even though we can't find a formula for it that's a nice function. It involved the Bessel and gamma functions. It helps you believe it. But to believe it more generally, we need some theorems. We need existence theorems to believe solutions exist. Explicit solutions for implicit equations, or solutions of equations that you can't solve with ordinary means that don't involve simple functions. Maybe they involve functions whose names you've never heard of before. Maybe they're completely new and nobody's ever heard of them before. Nobody's ever given them names before. You could be the first person to name a certain solution of a differential equation. You could even name it after yourself. I could say it's the Kinney function. Of course, if I do that, it better be useful if anybody's going to care. So, but you can do it, okay? The implicit function theorem can, at least for the first example, the separable one that we did, the first example, be thought of as an existence theorem. That was the stuff where I talked about capital F equaling C and the partial derivative of capital F with respect to y being non-zero near the point in question. And by the way, where those slopes were vertical, that's actually where the implicit function theorem doesn't apply. In that graph, where the implicit solution that looked like an S had slopes that were infinite here and here, that's actually where the implicit function theorem does not apply. You might want to think about that. For that type of ODE, it gives conditions under which an explicit solution exists, even if it is hard or impossible to find an explicit formula for it. It's a very hard concept for people to get their minds around. We're so used to functions having to have formulas. But no, the function can exist even without a simple formula. All that's necessary is that the outputs are completely determined by the inputs over some domain. That's all that's necessary. It doesn't have to have a formula. But to know it exists is important, to know that we're studying something that exists for one thing, and to know we can approximate it. With Euler's method, for example, we can approximate it, and we can believe the slope field is giving us good information about the solutions. There are more general kind of existence theorems. Here's one that's good enough for us. This is our main one from our main textbook by Blanchard, Devaney, and Hall. I'm going to show you another one to close off lecture A here, 7A. Here it is in all its glory. Kind of complicated, of course. Existence theorem. Okay, theorems have hypotheses and they have conclusions. They have things you need to assume and things that follow from those assumptions when you know those assumptions happen to be true for particular examples. Suppose little f of t comma y, a multivariable calculus function of two variables, a right-hand side function for the differential equation, is continuous. It's a continuous function. There's the key assumption. Over some open rectangle. Why an open rectangle? It just keeps things simple is the reason. Set builder notation here. R is the set of all points, t comma y. I'm implicitly assuming we're using rectangular coordinates here. Of course, I could draw them in polar coordinates, and then it wouldn't look like a rectangle, but we're not doing that here. Where t is between two numbers a and b, and y is between two numbers c and d. This is also an alternative notation for that. This is Cartesian product notation. I did briefly mention that before. This interval, Cartesian product with this interval, means we're considering all points where the first coordinate is in this interval and the second one is in this interval. You can look it up, Cartesian product. In the ty plane. So we can draw a little picture here. Hopefully it'll let me draw it. And maybe A is here, and B is here, and C is here, and D is here. And we're talking about all the points inside this dashed rectangle that I'm making. It's like a viewing window on the calculator. It's open because these are strict inequalities, less thans versus less than or equal to's. So it's all the points inside the rectangle, not necessarily on the bound, not on the boundary. And t0 comma y0 is going to be a point in that rectangle. Remember, this means in, or is an element of is the more official way. So t0, y0 is just some point in there, maybe right there, somewhere in there. We don't want it to be a closed rectangle because we don't want it to be on the boundary for some technical reasons. Okay. R could be the entire plane, or it could be a really small rectangle. It's possible. It's real small. We only need the function to be continuous on R. That's the hypothesis there. When you see the word then you are alerted to the fact that now we're going to say the conclusion. And then there exists a possibly very small number, epsilon greater than 0. Epsilon is the mathematician's favorite Greek letter for small numbers. And a function phi of t defined for t between t0 minus epsilon and t0 plus epsilon, possibly some very tiny interval centered on t0. That solves the IVP. And there's a typo here. This should be a t0. dy dt equals f of t y, y of t0 equals y0. In other words, we can say that the left-hand side when you plug in phi, which is phi prime, equals the right-hand side when you plug in phi in place of y, not in place of t. So I replace the y with phi of t. Left-hand side equals right-hand side for all t in the interval. This is interval notation here. Yeah, I wanted to mention that earlier. You don't want to get confused between intervals and points. They use the same notation. This is a point here, t comma y. This is an interval, this is an interval, this is an interval, open intervals. The notation is the same, the meaning is different. You pay attention to context to know what meaning is being used. And the initial condition is satisfied too. So epsilon could be tiny. This interval could be some tiny interval around t0 here. I'm not going to try to draw it because I just can't draw it fine enough here. And the solution would exist on that little interval. It could be a bigger interval. It could be something big. It could be the entire real number line. Effectively, epsilon could be infinity. But in theory, if you're only assuming continuity of f on this rectangle, it could be a very small interval. Now that's good enough for us for most situations. I'm going to end this lecture by backtracking a bit. This is the last slide for lecture A. And saying that you actually already know about existence theorems for differential equations. You just never knew it. If you've taken calculus before, you know about it. What in the world? You actually know an existence theorem for differential equations. It is the fundamental theorem of calculus in its second form. Second fundamental theorem of calculus. Actually, some people call this the first fundamental theorem of calculus. It gets really confusing that way. Most books call it the second one. The thing that most books call the first fundamental theorem of calculus tells you how to integrate functions from a to b. If you integrate little f from a to b, you do capital F of b minus capital F of a, where capital F is an antiderivative of little f. The second fundamental theorem is a little bit harder, but it does guarantee the existence of solutions. We'll talk about it here to close off this lecture. When the right-hand side function of the differential equation is continuous. We're talking about pure antiderivative problem here. Another typo. Same typo as before. I want this to be a t0 here. It's a pure antiderivative problem. The right-hand side only depends on t. It's not autonomous. It's not a function of y. It's not mixed. It's not an f of t comma y. It's just a pure f of t. It's just a calculus problem. Just integrate it to find the answer. And the fundamental theorem of calculus in its second form is what guarantees that you can do that if little f is continuous. So here's what it says. Suppose little f is continuous on some interval from a to b. This is closed interval from a to b. We could use an open interval there, using a closed one. And t0 is in the interval. t0 could be an endpoint in this case. And even, most typically it would be a, but even actually could be b. Though the meaning of the integral would be confusing in that situation. Define a new function. I could have just called this phi of t, but I called it phi sub y0 of t to emphasize the initial condition is y0. Phi sub y0 of t is y0 plus the integral from t0 to t of f of u du. What in the world? Keep your wits about you here. This is a definite integral for any fixed value of t. t0 is certainly fixed. If I pretend t is fixed, this is some specific integral, some specific number. Continuous functions are integrable. The integral will exist, and then I can add y0. If you define that function, that will be a solution of this IVP. This function is differentiable, its derivative exists, and satisfies this IVP. dy dt equals f of t, y of t0 equals y0. For all t in the entire closed interval from a to b. In other words, yeah, the derivative is always little f for all t, and it satisfies the initial condition. The initial condition is easy. Just replace t with t0, and you get the integral from t0 to t0, which is 0, plus y0 is y0. But it's the fact that the derivative of this thing is the integrand function, little f, that's the hard part, sometimes written in this form, d dt of this function of t. Yeah, when you think about the integral, you think about t being fixed, but then you say, hey, I can plug in anything for t. This is really a function of t. Of course, differentiating a constant gives you 0. Differentiating this integral, it's like the d dt and the integral sign cancel out to give you the integrand function, the little f. It's like they're inverse operations. Okay? To not be confused when you think about this, you've got to think about it in the right way. For any fixed t, I can find the integral. I get a number. This then defines a function of t that may not have a simple formula. Might be a Bessel function. It's got a formula involving an integral that doesn't involve a Bessel function necessarily, but if you actually found an antiderivative, it might involve a Bessel function. And I want to differentiate that function with respect to the upper limit of the integral. I get the original integrand, but I need to put a t instead of a u. The u is just a dummy variable, doesn't have any meaning, I just need to pick something different than t. I should probably warn you that many scientists go ahead and put a t there and there anyway, but really the t should be in the upper limit of the integral. And yes, that is the end of lecture 7a.